Hello and welcome back. Today we will start discussing a specific type of problem where we want to achieve privacy, and this would be in a buyer-seller context, and this will lead to an interesting mechanism for achieving privacy called the exponential mechanism. We will talk about this, and after talking about this we will move on to privacy in machine learning and see how you can make machine learning algorithms private. Okay, so what is the context that we are interested in? So let's say we have a digital, some digital good. Let's say this can be like a painting, right? So I'm just drawing a painting here. Let's say this is the artwork which I'm interested in selling. Now I have n different buyers for this. Let's say buyers, there are n different buyers for this, and I want to kind of get their valuations. How much are they willing to pay for this particular artwork, right? So let's call those valuations V1 to Vn. Now remember, this is a digital good, right? So this is which means that I can sell copies of this to multiple people, right? So what does valuation mean? Valuation just means that how much amount is each person willing to pay for this particular product, right? So now my goal as a planner is to set some price for this product so that I kind of make profit. Now how will I set the price? So how to set price? Well, what will I do? Now if I set price P, let's say there is some value P, 100 rupees I set for this particular digital art. Now how much will I make as revenue? Well, I will look at the valuations, and everybody who is willing to pay at least 100 rupees will buy this if I set the price as 100 rupees. And everybody who is set, whose valuation is less than, strictly less than 100 rupees, will not buy this price, will not buy this artwork, because their valuation for this is lower than my price. So if I set price to be P, then my revenue is just, you know, P times sum over I equals 1 to n, well, indicator of Vi greater than or equal to P. What does this mean? This is just an indicator function. This is just saying whether this proposition Vi greater than or equal to P is true or false. If it is true, this will take a value 1. If it is false, this will take a value 0. Essentially, this is saying that, you know, this can be thought of as number of buyers whose valuation is greater than or equal to P. If there are 10 people whose valuation is greater than or equal to 100 rupees, then I make 100 into 10, 1000 rupees, right? So because I will sell it for 1000 rupees, that's the price I set, and 10 people are willing to buy it. Now, so this is the setup, right? So I need to set my price, and of course I want to make profit, so I will set a price P such that this value, the revenue that I get, is as high as possible. So what is the privacy question here? The privacy question here is that the people who are giving me their valuations want their valuations to be protected, right? So they don't want anybody else to know their valuation. Like how we had the survey example earlier, where, you know, you wanted to protect the fact whether you voted or not, or whether you have a particular disease if you are in the hospital example. Here the valuation, my valuation for this digital art needs to be protected. But what becomes public to the world is the price, right? So everybody sees the price. So now so let's look at this slightly carefully with an example, right? So here is an example. Maybe I'll go to the next page. Example. Again, we are in the same thing. So we have this digital good, and there are three, let's say 3 buyers who have signed up for this, and their valuations are 10, 10 and 500 respectively. There are 2 people who are willing to pay 10 bucks for this digital art, and there is one guy who is willing to pay 500 for this. So now I want to understand, as a planner, as somebody who is selling this digital art, how does my price versus revenue plot look like, right? So price starts at 0 and then I can keep increasing it. Now it's a simple exercise for you. I mean, if you want to pause and think, do try to plot this graph for yourself, right? So I'm going to tell you what this graph looks like, but it's not too hard to calculate. Now, until the price becomes 10 rupees, my how much will I make money? Well, if it is, let's say, 1 rupee, then all 3 people are happy buying it. If it is 2 rupees, everybody is happy buying it. If it is 10 rupees, again everybody is happy buying it, right? So which means that if I set the price as 2, then my revenue is going to be 2 times 3, which is 6 rupees. If they set the price as 5, my revenue is going to be 5 times 3, 15. So which means that this is going to be, you know, a curve with slope of 3 until 10. Right. So, and this value is just going to be 30 rupees. Agreed? Because until then all 3 will buy. So, I will make thrice the price that I set as my revenue. Now, the moment it crosses 10, what happens? What happens is that 2 people are saying, no, I am not going to buy this anymore, right? So, I do not want to buy this anymore, and so your revenue goes down, because there is only one guy who is willing to buy, even if it is about 10 rupees, and so your revenue is just going to drop immediately to 10 plus whatever that value is, right? So how much ever you are increasing it, and it's going to go with, because there is just going to be one person after this who is willing to buy, and until my price, you know, becomes, let's say, 500, it's only that person who will buy this. So, and so my, it's going to grow with a slope of 1, because there is only one person. How much ever I set the price, that's the revenue that I get until the price hits 500. Now, after 500, it just becomes 0, because nobody is going to buy it. So, my revenue, which is what I want to maximize, is a function which is very haphazard, right? So, the revenue function is very haphazard. Now, what happens is, think of this. So let's say I set a price, right? So, in this case, if I want to maximize my revenue, what price will I set? Well, obviously the price that I am going to set is going to be 500, because there will be one person who will buy it, and I am happy, right? So, now if I want to protect the valuations, right? So, if I add, let's say, Laplacian noise to this price that I am setting, and I set a different price, now what happens is, couple of things happen, right? So, one thing is, what does that mean? That means that 500 is the price that I want to set, but I want to protect the valuations. So, I will add some noise to this, and if it is a Laplacian noise, which means that I am going to add something to 500, and then, you know, if you, I mean, I am going to reuse the same plot to draw the PDF. So, the PDF of Laplacian will kind of go down like this, right. So, and now here is some price which is at 30, right. So, where is 30? 30 will be somewhere here. Now, at 30, what is the revenue? The revenue is still 30. Now, if I am adding 500 plus Laplacian noise to set my price, now, well, at a value of 30, I will choose that value of 30 with certain probability. Now, had I set my price to 10, my revenue is still 30, but the probability of setting 10 is much lower than the probability of setting my price as 30 under the Laplace mechanism, though the revenue is the same, right. So, these two price points 10 and 30 to me are indistinguishable as a seller, right. So, because to me does not matter whether I set 10 or whether I set 30, I am going to make the same revenue, but the chance of one of these prices is higher than another. 30 has higher probability of being chosen than 10, right. So, we want to avoid this situation, right. So, and the question is how is there a natural way to avoid the situation at the same time protecting the valuations? And the answer is yes, and we are going to see a simple technique to do this, which is called the exponential mechanism. So, this is the topic. And just to formalize, so we still have x in xn, let us say, which are the valuations, like how we were protecting the binary values earlier. So, now we will protect the valuations. These are the valuations. Think of these as 10, 10 and 500 in the previous example. Now, let us say we have a set of prices, right. So, from which come from some finite set of prices, and we have a scoring function. What is the scoring function? Say, well, given a set of valuations and a price, the scoring function will tell me what is the revenue. Think of this as revenue, right. So, revenue function. Right. So, if I tell you this is the set of valuations 10, 10 and 500, and if I set a price to be some, let us say 300, then I will know that I can apply the formula that how many people are above 300, whose valuation is above 300, and then multiply it by the price itself, right. So, P times whatever that we saw earlier, right. So, P times sum over I equals 1 to n indicator of Vi greater than or equal to P. This is my valuation function essentially, right. So, that is I am going to think of this as scoring function. Now, I want to protect my valuations in an epsilon private differentially private manner, and for that I am going to define my sensitivity slightly differently, but in a natural way, as the max over all prices that I could possibly set, max over x comma x prime in xn, two sets of valuations, the absolute difference between the revenue that I will get from x versus the revenue I will get from x prime, right. So, this basically you take any two sets of valuations and then change one valuation. One person changes his or her valuation, and now among all prices that I can set, how much does the valuation change, right. So, what is the sensitivity of the revenue if one valuation changes, and that is what I am going to set as my sensitivity. And now the exponential mechanism says, and I will put down the mechanism and talk about this a bit. This was by I think in 2012 by Talwar and others, and the mechanism is simple. So, select your price, select price h belonging to the set of all price h with probability proportional to e power epsilon by 2 delta s of x comma h. Essentially, this is telling me that if I want to choose a price, then I am going to probabilistically choose a price. Earlier, we said that, well, one way to do this would be, I will compute which is where I get the highest revenue, and then add some noise to that price and set that price, right. So, that is what I was saying earlier, and that is a very tricky thing to do, right. So, one thing is that, if I add noise and the noise goes to the right hand side, then I actually make no money, right. So, zero money. Now, on the other hand, if I do it to the left hand side, there are different prices for which I would have made the same revenue, but one is less probable than the other, which is also not so satisfying. But what the exponential mechanism is saying is that, well, choose a price, h is some price, right. So, choose that price proportional with some probability proportional to epsilon by 2 delta, and the more important thing is the revenue that price will give you for the data set. You have a data set, and for every price there is a revenue, right. So, which means that in the picture earlier, so for price 10 I would have gotten a revenue of 30, for price 30 I will still get a revenue of 30, which means that the probability with which I will choose 10 or I choose 30 is the same. It depends not on the price, right. So, I am not adding noise to the price, I am choosing a price based on the probability of the revenue that I will earn because of this. And if I do that, then I will get the same probability for two different prices which give me the same revenue, right. And that is the kind of advantage of this, right. So, now we are treating all prices equally likely as long as they earn the same revenue. Now, one can show that exponential mechanism EM is epsilon differentially private for the valuations, right. So, which means that I am happy to give my valuation out to the trusted curator, because even if the trusted curator gets my valuation and is not going to release the valuation or some function of valuation, but then is going to release a price value to the world, and from that price value you should not be able to figure out anything about the valuations for neighboring data sets. That is the guarantee that I want, right. So, the public value here is the price, and all other, let us say everybody else colludes, all the among the n buyers, n minus 1 buyers are collaborators, one guy is separate, right. So, now these n minus 1 collaborators know their own valuations, and now they want to figure out what is the valuation of the nth buyer. Well, the nth buyer now still has the guarantee that by giving his value to the trusted curator and the curator releasing the price to the world, these n minus 1 guys, even though they are collaborating, will not be able to figure out what is the nth buyer's valuation, up to of course epsilon differential privacy as usual. So, that is the privacy guarantee. The utility guarantee, again I will make a small note on this. The utility guarantee is as follows. The chance that, and I will write this and then we will talk about this, the revenue that I will get if I set my price according to the exponential mechanism, right. So, is at most opt of x, and we will talk about this in a minute, minus something that is not so important, but we will just put this down. So, this is the utility guarantee for this exponential mechanism. Again, I will highlight the key things that are required here to understand this better. So, you have a data set, and this is the price that gets set via the exponential mechanism. If you set a price via the exponential mechanism, that is, for every price you look at the revenue and you set a price proportional to e to the minus epsilon by 2 delta into revenue. That is the price that you are setting, and now you get some revenue because of this, and that revenue is a random quantity. Why is it random quantity? Because the exponential mechanism is random. It is setting a price proportional with some probability proportional to something, right. So, EM of x is a price value, but then it is a random variable because each price has a different probability of being chosen. So, which means that the revenue is also a random quantity. And now we want to ask, how bad is this random quantity with respect to opt of x, which is the maximum revenue I could have earned, that could have been achieved, right. So, given the valuations, I can set price optimally, right. So, in the previous example, when you had 10, 10, 500, 500 was the optimal price that to set, because that would give me the maximum revenue. But instead of that, we are saying we are choosing a price via the exponential mechanism, and then we are asking, well, how much is it worse than setting it via, you know, via setting it as 500 as the optimal price. And now what we are saying is that the chance that the revenue that I earn via the exponential mechanism, by setting a price via the exponential mechanism, is not too less than the optimal value that I will earn, that I can hope to achieve. And how much? Well, how much will I lose? Well, the chance that it is too less than the optimal value, right. So, let us say this is where opt of x is. Now, I am going to lose some quantity, which is 2 delta by epsilon ln h, cardinality of h plus t, that is some quantity. Think of that as some quantity, and now let us say that quantity is this much, right. So, this much, and now I am saying the chance that the revenue that my mechanism will earn me is less than this, right. So, the chance that I will end up with a revenue here is small, which means that with very high chance I am going to be within this range, right. So, high chance, right. So, this is the revenue scale basically, and this is the highest amount of revenue achievable. But what I am saying is that, with very high chance I am going to get a revenue which is not too less than the optimal revenue that I could achieve. Of course, I will not achieve the maximum because I have added noise. So, I am setting a suboptimal price, but how suboptimal? Not too much, which is the utility quantity, right. So, I do not want to lose out so much on that 500 rupees that I might have gotten. So, I will kind of get a reasonable amount of price, right. So, that is what this the exponential mechanisms guarantees. Okay. So, this is a very popular mechanism, and so I just wanted to highlight this in this course as well. So, just to set context as to where we are so far. So, we started with randomized response, then we looked at epsilon differential privacy, then we looked at approximate differential privacy, epsilon delta differential privacy using the Gaussian mechanism, and we looked at some properties of Gaussian mechanism, including composition and post processing. And now we are looking at exponential mechanism, where instead of releasing instead of releasing the revenue, you are releasing a price which is some function of the valuation, and we want to protect the valuation, and you can use an exponential mechanism. This is a very general thing, not just for the buyer seller thing. So, you have any xn any data set of, and then you have a set of prices, right. So, a set of quantities that you will release, and then there is something that connects the input and what you are releasing using the scoring function S. In this case, it happens to be the revenue function. Then you can use the exponential mechanism. The buyer seller market is a typical example where this can happen. Now, here also you can achieve epsilon differential privacy and a reasonably good accuracy. That is, you won't be off from the optimal value by too much. So, this completes the exponential mechanism part of it. We will now, in the next video, we will start looking at privacy in a machine learning context. And the moment we have understood all this, putting this in a machine learning context will become very easy, as we will see in the next video. So, see you again in the next video. Thank you.